Well, hello and welcome. My name is Jamie Reilly. I'm a professor of communication sciences and disorders and psychology at Temple University in Philadelphia. Today I'll be telling you a little bit about the two mountains problem, a way I've been looking at some of the measurement problems and some answers to questions about cognitive pupillometry. Let's get right to it. So, for many of us who are pretty familiar with this method at this point, we can look back and say, well, how do we learn about pupillometry? We look to the seminal studies of Hess and Polt, Kahneman in the 1960s, early 1970s, that first showed that the pupil moved in conjunction with factors such as cognitive effort and arousal and interest level. So when we look at one of the first studies that really showed this effect was Hess and Polt in 1960, which actually showed these sex effects. When females and males were viewing pictures of babies, pictures of mother and baby, nude males, nude females, versus the control of landscapes. And so this paper got extreme amount of interest because it showed that the pupil parametrically modulated with interest level, the interest level of participants, right? So this introduced pupillometry to modern psychology. Now, why I bring this up is that this recent paper, it's a preprint now, but it's gotten tons of interest on ResearchGate, has shown that, has done a very, very tight replication of many of the studies of Hess and Polt, and shown that many of them aren't replicating very well, which is basically the foundation of this field. So, this with the question of why, gets to really one of the important issues in this field, that it faces many of the same measurement challenges that are endemic to all of experimental psychology, and that are underlying the replication crisis. We're going to talk about some of those challenges and how we might settle them, and then open questions in cognitive pupillometry research. So the way I've been thinking about this is it's an extremely complex methodology with many questions and issues that have really not been empirically worked out very well. But the way I think of it is just using a much more simple metaphor than the computational complexity that involves complex time series. Really, what pupillometry boils down to is comparing two aggregate mountains and saying, okay, is one mountain higher or bigger or larger than another, right? And so what I want to use is this metaphor of comparing two mountains, right? And so I want you as a listener to imagine that you are a geographer working on this fictional two-dimensional planet. That has two mountain ranges, the Hornbill Range and the Ibis Range. And your task is to figure out, okay, which of these mountain ranges is higher or better or bigger? There are some problems with that. The Ibis Range, you can see, starts under the sea. The Hornbill Range looks like it's higher, but maybe the Ibis Mountains have a higher base to peak. So you have to figure out some way to answer that question, that fundamental question of which of the mountains are larger, right? Which is basically the same problem as pupillometry. So what do you do to figure out the two mountain problem? Which mountains are higher and bigger? Well, one is you can send out drones and submarines. So you send out your submarine to the Ibis Range, and you get lots and lots of samples of this. These latent variables that are data points that you can then interpolate across to figure out a profile of each mountain in the range. So the more sampling you're going to do, the better. But you're always going to face problems, right? So you send up the drones. There's going to be high winds. So some mountains you're not going to be able to sample. You send down the submarine. There's going to be crazy sea monsters that take us. You're going to have missing data. So lots and lots of assumptions about interpolating across points, similar to what you would experience in pupillometry. So the first thing, you send out, you get your data, you then interpolate it, you come up with reasonable estimates of mountains after you've imputed missing data, and then you average the mountains in the Ibis Range and the Hornbill Range, right? And so at the bottom, what you see here are basically what you can say is some confidence interval around an interpolated average. So you have an average mountain for the ibis range and an average mountain for the hornbill range. And those averages are corrected for where the mountains start, right? So some start at sea level, but some start much higher. Here you've corrected for the baseline of where they've started. You can apply binning, so you can say like, okay, in this range from 0 to 0.5 kilometers, here's what the average height is. And you can still then, you can get a comparison of the mountains so you can answer your question. Now, when it boils down to it, you can say, well, what are the information that I need to describe whether two mountains are different, right? So one is you can describe how high the mountains are from base to peak, right? And so here, this is a common measure that we use in pupillometry, which is peak amplitude or peak dilation, time locked to the onset of events, right? So you can say, okay, base to peak altitude is one parameter that we can describe. You can also say this horizontal distance of here, if you're looking at here, is a measure of dispersion of how long it takes to get to peak, right? And that's a variable in pupillometry we call time to peak. You can also measure this in terms of horizontal distance to the baseline. That is, you have a rise and then a decay back to where you started, right? You can measure that distance. And to some extent, these variables together are encapsulated under the total area under the curve, right? So you have an event, or, when we're still talking about mountains, not events, but the mountain goes up, it comes down. You can measure the total area under the curve under the mountain. And then you can measure the average altitude across the mountain, right? So these are 5 different parameters or 5 different ways of describing two mountains. And each tells us a little bit of different information about the mountain. Now, let's talk about how this metaphor applies to pupillometry research. Well, many of us, when we do studies in pupillometry, we do event-related designs. And event-related designs involving, you have stimuli, many of which are modeled as delta functions. And a delta function is such that the stimulus onset is infinitesimally short. And you have an event that is evoked. You have a stimulus that's evoked from that event, right? So what you have here is raw data from a single subject time series of continuous recording of pupil data. And what I have here in the red and green are the onsets of the marked events, right? And so when you look at a raw time series of pupil data, it's very, very difficult to pick up any discernible patterns, right? So these are the onsets of one condition read relative to another. And in this case, this is just this is one person listening to true and false statements about the world. Paris is the capital of England versus London is the capital of England, and versus true and false statements about yourself. Your name is Mary versus your name is John. And looking at evoked responses to true and false statements about the world. So with that, the idea would be you have mountain ranges, and you have 2 mountain ranges, one corresponding to the red questions and one corresponding to the green questions, interspersed within each other in a time series. You need to extract those mountains and figure out ways to compare them. Now, when you look at the raw data, what you can see here is you have a fairly stationary time series, right? So if you were to draw a line straight across, you don't have anything that's really descending or ascending. When you would see that in pupillometry would be when there's increases in either a tonic arousal across the session, or when the baseline luminance in the testing room changed, right? So, if you started something around here, and you have the light got much darker and you dilate it over time. So that would be a non-stationary time series where the dilation is progressively going up, and then you have the events embedded within that. Here on the y-axis, you of course have pupil diameter, and with many of us who use eye trackers like iLink, that reports the data in arbitrary units. And we're going to talk about this soon, about the need for really sort of when we talk about replicating, converting those arbitrary units to a human-like measure like millimeters or millimeters squared for area. Okay, so let's get into this a bit. A person recently in a scientific meeting, I said to me about pupillometry that said, I think pupillometry is pretty easy. When you run an eye tracking study, you just get pupil diameter for free. And basically the complaint was, I don't see why it's so difficult. Now, this is a person who doesn't do pupillometry research and does eye tracking research. And as you'll know, many of us who use eye trackers for things like visual world paradigms and things like that, you look at the data and you have a vector of right and left eye pupil diameter. And you could argue, okay, well, you can use that data and just do a pupillometry study. So there are lots of compelling reasons to doubt this claim, that it's just you get the data for free, and that pupillometry really doesn't need that many considerations to do the study. One is that the task-evoked pupil response indexes very, very small physiological movements. So when we look at the pupillary changes in the pupillary light evoked by the pupillary light reflex or dark reflex, we have a dynamic range of the pupil response between about 2 and 9 millimeters. When we look at task-evoked pupil responses, these are responses evoked by cognitive demand and not luminance shifts. They are on about the average of 0.1 millimeters, so very, very small, an order of magnitude less than what you would see in a luminance shift. There are many, so another complicating matter in pupillometry is that there are many sources of anatomical variation and potential environmental confounds. So there's a lot of factors that cause what could look like task-evoked pupil responses that are really actually task-correlated variables, like the onset of a stimulus producing a luminance shift, or producing surprise, or producing an acoustic startle reflex, or just interest, or things like things that are counterintuitive that you never thought, jaw clenching, blinks being correlated with the onset of events, right? So there's lots and lots of thinking that really needs to go into, and planning that needs to go into a well-designed pupillometry study. And then more planning steps happen in the data processing and analysis, so that we're going to talk about that soon. And then what conclusions and inferences can you make from a pupillometry study is also a complicating variable. So I would argue to this person that pupillometry is not a very easy modality to study. It takes a lot of careful planning to get a really good pupillometry study, which again, I think is why when we look at the methods in this field, the methods are all over the place. And replication is really something that is very, very rarely done in this field. So again, I'll return to that. Okay. So let's talk then about factors. So when we talk about the necessity for careful planning, there's necessity for careful planning both before, during, and after a pupillometry study. If you haven't read this article from 1975 from Warren Tryon, it's basically a list of factors that you really need to consider about sources of variability that look like they're causing a task-evoked pupil response, but really have nothing to do with the variable of interest. So, many of us here are interested in things like a cognitive load related to upregulation of attention while you're hearing speech that is degraded. But Tryon notes all of these other factors that look like something that cognitive load, but aren't. So things like blinks are often task correlated, right? So the other thing that happens when you have an executively demanding task, people blink more. And those blinks happen right at the onset of stimuli. So when you have these packages like Jason Geller's package, Gazer, that really do a great job of interpolating across blinks and missing data, it doesn't take care of the fact that those blinks are happening right when you need to model the data most, or right when you have it the most executively demanding part of your task. Same with pupillary light and dark reflexes happening right at the onset or shift between your stimuli. And then factors that almost no one considers. So things like even your iris color and contrast between the color of your iris and the darkness of your pupil make a difference. So things like weird factors you wouldn't even think about. So like blue eyes that show different rates of constriction than darker color pigment irises. Incentives and motivation is another one. So the fact that designing your study so that you're building in incentives and motivation. Many pupillometry studies involve really, really boring, lots and lots of trials of hearing, say, a tone, and people just zone out. They can't do it. And so when you look at that and you factor in things like fatigue waves, boredom, and so basically people going into the resting state. It's something that you have to build into your design. Lots of breaks and keeping it exciting. And even, as Drew and Jonathan will probably talk about, interacting with participants a bit while they're doing the experiment. So there are also other factors that try and identify variable levels of tonic arousal vary throughout the day. So people are different during the morning than they are in the afternoon. Just circadian rhythms change. And then factors that, people really don't think about a lot, like coffee drinking, so caffeine and drugs, so drugs that many of us take, influence the pupil response. The choice of determining monocular or binocular eye tracking and ocular dominance, which eye should we model, is also an open question. And then how do we implement appropriate baselines or do baseline correction? And we're going to talk methods-wise. That's something that my lab has done a bit about in how we scale responses, whether we should use linear scaling or nonlinear scaling, which I'm going to talk about in a minute. So these are all factors that you need to consider before. And if you haven't read the Warren Tryon's article, I think it's a very good classic sort of benchmark of that you should go to, because it's really just listed out like here's what you need to think about: caffeine and iris color and all of these things that I never thought about before, but are really sort of important. So that's before to your design, right? So some important factors to consider before your design, and then factors to consider during your design. So one is this idea of idiosyncratic luminance changes, right? So one of the things that is kind of interesting about this, so people always talk about the necessity for matching very, very closely on luminance, maintaining isoluminance across stimuli. And I'm going to argue that's not incredibly important if you do good baseline correction. In that, this idea that we are interested in relative change from a baseline to from a baseline of a stimulus to some evoked activity. And if you have higher levels of luminance in one condition relative to another, the baseline correction for that trial will correct for that difference. Now, the problem is, though, if you have idiosyncratic differences in luminance, I was thinking, okay, what would be the most idiosyncratic example of luminance just shifting randomly or stochastically that would influence that? And I was thinking, well, like a disco ball or a strobe light just happening. And so, I did what you would do, Wikipedia or Google Images, and I Googled disco ball, and then I found that there's actually a disco ball drone that you could fly around. So, I was thinking a disco ball would be crazy for luminance and doing pupillometry study, but that was like a disco ball drone that flies around would be even worse. So there is that exists. So don't do that. Don't have a disco ball drone in your testing room. But factors such as things that you wouldn't think of, like looking off center. Things like your pupil shape deforms when you look off center. So really having people fixated in the middle of your screen for long periods of time induces fatigue. But you need to have them looking dead on to get really good fidelity data. And again, this speaks to the issue of not getting data for free when you do an eye tracking study. When you do an eye tracking study, you're typically interested in ratios of saccades to fixations and people moving around. That's the last thing you want to do in a pupillometry study. So looking off center and distraction and sort of mind wandering and eye wandering it gives you very, very poor data fidelity in a pupillometry study. So these are all considerations. And then after, right? So one of the big things after is where the data crunching happens. So factors to consider after, you need to make a number of methodological decisions. And each one is not trivial. And each one people will disagree with. I think there's not good consensus on which methods we should be using. So how do we filter bad data, right? So how do we know that the data are bad? Low pass, high pass filters. How do we aggregate good data? Do we bin our data, or do we just do we leave it alone and model it using things like growth curve analysis? Many of the so the great thing about the world right now is that so many people are embracing open science and really putting out open source software packages. Dr. Dennison, I just discovered it has a package which I didn't know about, which sounds great. We've been using Jason Geller's package, Gazer, but there are others. CHAP and Pupillometry are other ones. So these will take care of some of the issues that you have in imputing missing data, but each one also incurs many of the assumptions, right? So things like velocity-based interpolation. You have to really know and be able to get under the hood of these packages to know what they're doing in processing your data, or else you won't be able to interpret the conclusion. So then one of the other big factors is, okay, well, you've got your data cleaned and into time series and extracted so that you have two mountains, one mountain for one condition and another mountain for the other one. Which parameters of those mountains are you really interested in comparing? Are you interested in comparing peak, time to peak, average amplitude, area under the curve? Each of those things really indexes different neurophysiological processes and cognitive processes. So figuring out which parameters you want to test and what does it mean, right? What does it mean to have a higher area of under the curve is also an open question. So then what I'm going to talk about now briefly is how to some data from our lab on how to baseline correct your data. Okay, so one of the big questions, and again, this gets to the replication issue in our field, is baseline scaling. So what is baseline scaling? So I have it here, an example of showing a stairwell, right? And so a stairwell would be, if you have, say, a rising or falling time series, and the beginning of the stair is the baseline amplitude. So let's say you were walking up the stairs, right? And the stairs, each step, the rise to the run, basically how the height of the stair goes up, each stair goes up to the amount of space that you have your foot on. Say it changes as the stairwell goes up. That would be a nonlinear system, right? So this idea that as you get higher, the stairs get smaller, right? So that's a nonlinear system, as opposed to, say, a linear system where the stair goes up and that ratio of the rise to the run of each stair stays exactly the same. So so that when we talk about pupillometry, the pupillometry again has this dynamic range from 2 to 9 millimeters. Now, depending where you start, if say your baseline pupil is 4 millimeters and you have some event, you scare someone and it goes up to 4.5 millimeters, that would be a raw change, an absolute value change of 0.5 millimeters. Now, there's two ways you can think of that change. One would be if you look at the raw change just as a subtraction, it's 0.5 millimeters. But there are many past studies, and we've looked at this, did a count of this, a rough count of it, basically 30 to 40% of studies before about 2010 used proportional baseline scaling, which is a nonlinear scaling technique. And what that would be is if you say, okay, we have a 0.5 millimeter change, but you started the baseline at 2 millimeters, that's a 25% change. But if you model the same raw change from 6 millimeters, it's an 8% change, right? So proportional scaling, you can have the same exact magnitude pupil response, but it's a very different proportion of change depending on where the baseline where you started. So you have to, in order to compare across participants with different baseline pupil sizes, you have to baseline correct for their starting size. Now the question is, how do you do it, right? One way you could do it would be using nonlinear baseline scaling techniques like proportional scaling. And the idea with this, it wouldn't necessarily be totally unreasonable to do this. Many biological signals have nonlinear response properties, and that follows the law of initial values, one of the sort of hallmarks of psychophysics. The idea with the law of initial values is that the amplitude of an evoked response dampens as a function of the baseline. And you can think a bit about this as in something like your heart rate, right? If your heart rate is very high, and so if you're frightened, let's say, and you're hyper aroused, and then a dog jumps out and barks at you, you're already high, your reaction to that is not going to be proportionately the same as if you were very, very low when a dog barked at you. Basically, your heart rate response to that is going to be much smaller than it was down below, right? And so that's a nonlinear response modality. You have much, much higher signal intensity boost lower on than you do it when the amplitude's already high. And that's modeled in things like hearing acuity, heart rate, galvanic skin response. And these are either, the way you would scale the response would be using proportional methods, or more likely with power functions, right? So many biological signals involve power functions. Some biological signals, however, scale pretty linearly. So when we look at things like the hemodynamic response function that we model in fMRI, the HRF, it tends to have canonical linear response properties. That is, basically, it's the same canonical response that looks a lot like a task-evoked pupil response, regardless of where you are in the brain and regardless of the signal amplitude where you're starting. And the good thing about that is it allows you to model the response using deconvolution techniques, using mathematical techniques that always look for the same shape of the signal. If it was nonlinear, the signal shape would change depending on where you started. So this is what linearity buys us, right? So it basically allows us to compare across different baseline pupil amplitudes. It allows us to compare across different luminance if we baseline correct for where someone started. So briefly, I'll talk a little bit about two experiments and looking at whether the pupil response scales linearly. In this paper, in Behavior Research Methods, we published last year, we looked at whether the pupil response scales linearly or non-linearly by manipulating the baseline pupil amplitude. So basically what we did is we did the reverse of what a normal pupillometry study is. And so the normal pupillometry study is, in experimental design, is you hold luminance constant so that you basically maintain a very stable baseline pupil amplitude, and then you manipulate some task demand, some cognitive task demand, right? Harder and easier, or two different conditions, easy or hard math problems, right? And so the idea is you look to see whether the cognitive manipulation did change the pupil response, right? So what we did in this experiment was we flipped that logic. We kept the cognitive task demands the same, but we changed the luminance. So we tested people in a dark room, a very, very dark room, or a very, very bright room, and we kept the task demands the same. People in this experiment, what they were doing was they were counting pure tones. So they were hearing sequences of pure tones, do 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 do, and they had to maintain a running count of what they were hearing to give you a count of the number of tones they heard at the end of it. And we modeled pupillary responses at each tone switch point. So the idea is people didn't know what we were doing, right? We were modeling the task-evoked pupil response at each switch point between tones, but we didn't really care about what they said about the count about the number of tones they heard. So in this, what we have is we have the baseline pupil response in the very dark conditions starting high, 5 millimeters or so, and in the very bright condition where the pupils are constricting, it starts very low. And we look at whether the evoked pupil responses are the same, whether they're the same whether you start in a bright room or a dark room. So when we do that, when we look at the data across 27 participants, this is the yellow is the bright condition and the black is the dark condition. They're very, very similar. So when we run Bayesian ANOVAs, there is basically no evidence for difference, no amplitude differences, no peak amplitude differences. So when we look here, it looks like they're somewhat a little bit different. Our reviewers were like, I don't know, that looks a little bit different to me, but they're not. So with that, the idea is when you look at the baseline, it looks like regardless of the baseline that you started, whether you start at 5 millimeters or 2.3 millimeters, you have the same raw total, basically raw or absolute value amplitude change of the pupil response, which suggests linearity. We did a follow-up experiment where we looked at 42 participants and we did a word monitoring task where we had people viewing streams of words, and they had to hit a button every time they saw one of the target words, which were boot, hawk, and desk. and we looked at foils in dark, in very, very dark, very medium, and very bright light. So we added a different condition. And so what we found here is the same exact thing, right? So when we do in the very bright light, the mid-tone light, and the dark light is equivalent. Regardless of the baseline pupil response that you started at, you show the same raw amplitude evoked change. And this suggests that there is that the pupil response, the task evoked pupil response, is linear and not nonlinear. And so, what does that mean? Well, if when we look at things like pupil studies that have done proportional scaling, I don't know what it means. It means probably a lot of them are wrong, right? And this gets to this issue of there's very, very little replication studies in pupillometry. I know of very few. And that really sort of, it's very difficult to trust when you look at a pupillometry study, whether it's right or not, which is, a fundamental issue. So I'm going to wrap up. Basically the summary of the research, some of our empirical research is that the task evoked pupil response does appear to be linear. And the conclusion with that is that you should use subtractive methods as opposed to nonlinear correction methods. And you should always baseline correct your data, I think. There are going to be, we can talk about alternatives using the growth curve and other convolution techniques. I think some of the other speakers are addressing that. And we'll be interested to discuss that. So the last thing, revisiting the tube mountain problem. I identified 5 different parameters or differences in talking about characterizing a mountain. The trick with this is we know very, very little about the neurophysiological correlates of each of those parameters. So we know that when there are hard math problems, your peak pupillary response is higher than goes a little bit higher. But we don't know that, we don't have a neurophysiological representation of what that means, right? So does it mean your locus coeruleus is working a little bit harder and sort of modulating the system? What does it mean to have a faster time to peak? What does it mean to have a longer decay? What does it mean that when we look at aging, the time to peak is lower and the peak amplitude is lower? We really don't have a firm idea, a good neurobiological model of what the components of the two mountain problem are. So when we choose these parameters, we're really sort of shooting in the dark about what it means, about what the biological representation of it means. We know it has something to do with effort, but it might also have something to do with arousal. It might have something to do with cognitive load. It might have something to do with surprise. It might have something to do with interest and motivation. And probably to some extent, there's shared variance across those, but we really don't have much knowledge about separating the two. So it's interesting, for a field that is, over 60 or so years old, it has a number, thousands and thousands of different studies. We really haven't done the foundational research in figuring out what exactly we are measuring. And so these are some of the open questions involved in that. I will leave it. I will leave it at that. And thank you for your attention. And I look forward to your questions. I thank you all. And these are some of the great people I work with, especially Dr. Peel. Thank you all.